Welcome back to Learn Math by Example. Today, we're diving into a fascinating challenge, crucial in fields like computer science and cryptography, proving mathematical claims. First, let's take a quick look at what we'll be covering today. We'll start with a real-life problem, then define some core concepts, work through the solution, and finally, wrap things up. Imagine the IB Math department is developing a new encryption algorithm. They've made a bold claim. For any three consecutive positive integers, say n plus 1, and n plus 2, if you take the square of the middle integer and subtract the product of the first and the third, you'll always get a specific constant value. This isn't just a guess. They need a rigorous, undeniable proof to implement this claim into their algorithm. Is this claim truly valid for any positive integer n? And how do you even begin to prove such a general statement? Now, this problem will be our guiding light as we explore the world of deductive proof and the subtle yet critical distinction between an inequality and an identity. Before we start with our encryption problem, let's solidify our understanding of some foundational concepts. First, what exactly is a simple deductive proof? Now, deductive proof is a method of showing that a statement is true by starting with known facts or premises and then applying a series of logical steps to reach a conclusion. Think of it like a mathematical domino effect. If the first domino falls and each subsequent domino is set up correctly, the last domino must fall. There is no room for doubt. The conclusion is guaranteed to be true if the premises and logic are sound. Let me tell you an exam tip. In your IB exams, deductive proof often involve carefully manipulating algebraic expression, applying geometric principles, or using established theorems. The key is to justify every single step you take. Don't just show the math, explain why you're doing it. Next, let's clarify a common point of confusion. The difference between the identity symbol equivalent and the equality symbol equal. The equality symbol is used when two expressions have the same value under specific conditions or for particular values of variables. For example, the statement x plus 2 is equal to 5 is an equality because it is true only when x is equal to 3. For any other value, this statement is false. You solve equalities to find those specific values. In contrast, the identity symbol equivalent is used when two expressions are equivalent and have the same value for all permissible values of the variables involved. Take x plus 1 squared is equivalent to x squared plus 2x plus 1. If you expand the left side, you'll always get the right side, no matter what value you substitute for x. An identity is essentially a statement that is always true whatever the value of x, due to its fundamental algebraic structure. Let me give you another example tip. It's crucial to use the correct symbol. Using an equality sign when you mean an identity can imply you're trying to solve for a variable rather than proving universal equivalence. Pay attention to this detail in your proofs. Alright, now let's put our knowledge into practice and solve the IB encryption problem. Our problem wants us to prove that for any three consecutive positive integers, say n plus 1 and n plus 2, the square of the middle integer minus the product of the first and the third always yields a constant value. Let's set up an expression based on the problem description. We have n plus 1, and n plus 2. Now the square of the middle integer is n plus 1 squared. The product of the first and the third is n into n plus 2. So we need just to evaluate n plus 1 squared minus n into n plus 2. This is a deductive proof, so we'll use algebraic manipulation. First, let's expand the squared term. N plus 1 squared is n squared plus 2n plus 1. And remember that it is an identity, so we can always replace one by another. Now let's expand the product term, n into n plus 2. Now distributing n, we get n squared plus 2n. Again, this is also an identity. If we substitute now the expanded forms back into our original expression, we get n squared plus 2n plus 1 minus n squared plus 2n. So the expression becomes n squared plus 2n plus 1 minus n squared minus 2n after we distribute the minus on the second term. Now let's group the like terms. We know that we have n squared minus n squared, they cancel each other. And we have 2n minus 2n, they also cancel each other. What remains now is 1. So we have deductively proven that for any 3 consecutive positive integers, the square of the middle integer minus the product of the first and the third always equal to 1. Since this statement holds true for all permissible values of n, which in this case are all positive integers, it is an identity. And we can write this formally as n plus 1 squared minus n into n plus 2 is equivalent to 1. So the IB Math Department's claim is indeed true and can be rigorously proven. For example, if n is equal to 5, the integers are 5, 6, and 7. Then 6 squared minus 5 times 7 will give us 36 minus 35, which is 1. So it works. Mastering proofs is a cornerstone of higher level mathematics. To get more practice and check your understanding, head over to our website to do more practice problems on deductive proofs. The link is in the description below. Don't forget, discussion is a crucial part of learning. So if you have any questions or comments, feel free to leave them below. We'll reply to them as soon as possible. In our next lesson, we'll explore more examples on simple proof. Make sure you don't miss it. Thank you for watching and see you next time.